Hello. Good morning, everyone.
Good morning, ma'am.
So, let's begin our session now. So, today we are going to start unit number 4. So, this unit deals with probability and base learning. Base learning provides a probabilistic approach to inference. It is actually the basis for learning algorithms that directly manipulates probabilities, as well as it provides a framework for analyzing the operations of the algorithms that do not explicitly manipulate probabilities. So based on this probability theory, it is possible for us to model machine learning problems. And that is why we are going to learn this. What we are going to cover in this unit? We are going to have a quick recap of probability concepts initially, because probability theory is required in all the concepts those we are going to learn in this unit. So let us have a quick recap of that first. Then we are going to see Bayes theorem. Under Bayesian learning, we are going to learn concept learning, learning a real valued function, Bayes optimal classifier, Gibbs algorithm. Then we are focusing upon the popular classifier known as naive Bayes classifier, and then we'll see few applications and case studies while discussing all those algorithms. So this is what we are going to learn in this unit. So let's begin with the probability theory, right? So I know you must have learned statistics and probability, right? And you know all those concepts. But let us revise those concepts. So what is an event? Outcome of a random experiment is known as an event. For example, getting a getting a heads when we toss a coin is an event. Getting a 6 when we roll a fair die is also an event. So these are the examples of events. What is event? The outcome of a random experiment. The next term that we are going to see is sample space. So what we mean by sample space? It is the collection of all possible outcomes of an experiment. So we go on repeatedly performing the experiments, right? And we come up with various outcomes of that experiment. So the collection of all such possible outcomes of the experiment is known as a sample space. Next concept is union. So we know now what is event. So we can define an event. Let us assume that event is C of getting a 4 or 6 when we roll a fair die. So an event C is defined as getting a 4 or 6 when we roll a fair die. So let's see here, this event C is union of two different events. Event C is union of two different events. So what are those two events? Event A is getting a 4 when we roll a fair die, and event B is getting a 6. So if we are having these two events, event A getting a 4 and event B is getting a 6, then the union of these two events can be computed and we say that it is event C. So event C is the union of event A and B. So probability of event C is given as probability of A union B. Right? And if we use a Venn diagram to denote this union, we may probably show this union of two events A and B as shown in this figure. Right? Now, let's proceed with intersection of events. Let's assume that C is an event of getting a multiple of 2 and 3 when we throw a fair die. So what is C? It is an event of getting a multiple of 2 and 3. Okay? So we describe here event A as getting a multiple of 2 . So we describe event A as getting a multiple of 2 when we throw a fair die. And we may define event B as getting a multiple of 3 when we throw a fair die. Right? And what is C? C is the event of getting a multiple of 2 and 3 when we throw a fair die. Here, event C is an intersection of event A and B. Correct? Obviously, event C is an intersection of event A and event B. So, probabilities of these events are then defined as follows. So, see here, probability of C is given as probability of A intersection B. Right? Now, let's proceed. This is the Venn diagram of intersection. So, let's proceed now with disjoint events. So, what are disjoint events? Any two particular events cannot occur at the same time, then we say that these events are disjoint events. When any two particular events cannot occur at the same time, then we say that these events are disjoint events. Say for example, we are having a fair die and we have to throw this fair die only once. So it is allowed to throw the fair die only once. Right? Now, here event A is suppose getting a multiple of 3. Event A is getting a multiple of 3 and event B is getting a multiple of 5. Event A is getting a multiple of 3 and event B is getting a multiple of 5. So, we want that both these events A and B should occur together. So, is it possible that both of these events, event A and B, occur together? Because we are allowed to throw the die only once. And what we want? We want to have multiple of 3 and multiple of 5. That should be our outcome of the throw of a fair die. And we are allowed to throw the die only once. So is it possible that we can have both the events A and B occurring together. Yes. Let's try to find out the subspace for event A as well as event B. So we are having the sample space 1, 2, 3, 4, 5, 6. So what is the sample space? Sample space denotes all possible outcomes. Correct? So what we are trying to do? We are trying to throw a fair die only once. So whenever we throw a fair die, obviously we may get one of these numbers, either 1, 2, 3, 4, 5 or 6. Do you agree with me? Yes? Obviously, whenever we throw a fair die, then the possible outcome would be either 1, 2, 3, 4, 5 or 6. So this is our actual sample space. Right? Now, whenever we are talking about this event A, that means getting a multiple of 3. So if we talk about this event A getting a multiple of 3, then subspace of this event A would be 3 or 6. Right? Subspace of event A is 3 or 6. Because out of all those numbers in our sample space, the multiples of 3 are 3 and 6. So we are having that subspace for event A. Similarly, subspace for event B is 5 because this is the only number that is multiple of 5. Right? And what we want? We want that we should get multiple of 3 and multiple of 5 at the same time. These two events should occur together. So whether it is possible that at the same time we are getting 3, 6 or 5? No. Correct? Because there is no common element in these two subspaces. Right? So there is no case for which event A and B can occur together. And such events are called as disjoint events. Fine. So let's proceed now with independent events. Independent events. Suppose we are having two events now, event A and event B. So if the occurrence of event A doesn't affect the occurrence of event B, events are called independent events. I will repeat. If we are having two events A and B, and if the occurrence of event A doesn't affect the occurrence of event B, then these events are called as independent events. So these two events have nothing to do with one another. They do not influence one another. Right? So such events are called as independent events. So let us see few examples of independent events. Getting heads after tossing a coin and getting a 5 on a throw of a fair die. So what is event A? Getting heads after tossing a coin. And what is event B? Getting a 5 on a throw of a fair die. So whether these two events affect one another, getting heads after tossing a coin has nothing to do with getting a 5 on a throw of a fair die, right? So these two are totally independent events, right? Now, one more example, choosing a marble from a jar and getting heads after tossing a coin. Choosing a marble from a jar is one event, event A, and getting heads after tossing a coin. So once again, first event is not affecting or not influencing the other event, right? Because in first event, what we are trying to do? We are trying to choose a marble from a jar. And in the second event, we are tossing a coin and we are getting heads. So these two events, once again, are independent events. They do not affect one another, right? One more. Choosing a 3 card from a deck of cards, replacing it, and then choosing an ace as the second card. What we are trying to do? We are having a deck of cards, right? So in our deck of cards, we are having 52 cards. So the first event is described as choosing a 3 card from this deck of 52 cards, right? Once again, we are replacing that card in our deck. So once again, we are having 52 cards as it is. And then my event B is choosing an ace as the second card. So this is event B and this is event A. So whether these two events depend on one another, whether they affect one another. Yes. Are you getting me or not?
Yes, ma'am.
Right? So event A is choosing a 3 card from deck of cards. Then we are going to replace it once again so as to make our deck as it is. And then once again another event is choosing an ace as the second card. So these two events have nothing to do, or these two events do not affect the occurrence of one another. So event A doesn't affect the occurrence of event B. And that is why these two events, once again, we say that these are independent events. Dependent events.
But ma'am, here in last example you have given,
Yes.
you are taking the same deck of cards.
Yes.
So it is there is a possibility of coming the second card as a S card. So how can we say that this is an independent event?
See, what is my first event? My first event is choosing a 3 card from deck of cards. Right? So, I'm having 52 cards and out of these 52 cards, I'll be selecting card number 3. So we are having 4 suits, right? So I'll be having 4 cards, 3 cards, right? So what is my event? Choosing a 3 card from 52 cards. Is that correct? Now what I'm replacing that card. So I have selected one card initially and now I'm replacing that card in my deck. So once again, my deck is having 52 cards. I have not removed any card from my deck. So once again, whenever I go for event B, that is choosing an ace, right? I'll be choosing an ace out of 52 cards. So entire deck I am having. So whether in the outcome of the first event, Whether I have got card number 3 or any other card, it is not affecting what is the outcome of my event B. Are you getting me? Because I am having all 52 cards with me and I am picking a single card out of those 52 cards. So even though, so whatever may be my event, in this case my event A is choosing 3 cards from deck of cards. Right? So whatever is the outcome of this first event, right? I am replacing that card once again in my deck. Right? So once again I am having 52 cards.
Yes, ma'am. I got it.
Right? So this will not affect the outcome of my event B, that is choosing an ace as the second card. Correct?
Yes, ma'am.
Fine. Similarly, we are having one more example here. Rolling a 4 on a fair die and then rolling a 1 on a second roll of the die. Rolling a 4 on a fair die and then rolling a 1 on a second roll of the die. So whether these are affecting, this is event A and this is event B. So whether these two events or event A is affecting event B, I'm rolling the fair die for the first time, right, and getting 4. That is my event A. And what is my event B? Rolling the fair die once again, right, and getting 1. So whether I'm getting 4 on a fair die, that is event A, will affect getting 1 after a roll of the fair die. Whether event A will affect event B.
No, ma'am.
No. So once again, these two are independent events, right? So, in a sense, in each of these examples, the probability of outcome of the second event is not affected by the outcome of the first event. We'll repeat. The probability of outcome of the second event, that is event B, is not affected by the outcome of the first event, that is event A. So probability of event B is not affected by probability of event A. Right? So probability is not affected by, rather we may say here, instead of probability of A, we may say outcome of A. Right? So probability of B is not affected by outcome of event A. So these are the independent events. Now,
Ma'am,
yes.
ma'am, what if we have given natural numbers and we have to find multiples of 5? In that case, we get numbers like 15, 30, which are also multiples of 3. So what we can say from that?
Will you please repeat this question? This question is in connection with what?
Ma'am,
Yes.
we have given sets of natural number like
Yes.
1, 2, 3, and we have to find multiples of 5.
Okay.
In that we have numbers like 15 and 30, which are also multiples of 3.
Yes. Yes,
So
obviously.
means
So I think you are talking about this disjoint events.
Yes, yes, ma'am. Yes, ma'am.
See here, what are those disjoint events? We are talking about two events, A and B. Those occur together. Right? Now, you are saying that we have been provided with natural numbers. Right? So, and
Yes, ma'am.
your event A is getting multiple of
5.
5. So we are having set of natural numbers, right? According to you, event A is described as getting multiple of 5 and event B is getting multiple of, what is your
3.
event B? Multiple of 3, right? See, if we are having entire natural numbers as my subspace, then in this scenario, we do not say, or we will not say that these two events are disjoint.
Okay, ma'am.
Right? So it depends on my subspace. This is my subspace, or rather not subspace, sample space. What is my sample space?
Yes,
My sample space is entire set of natural numbers. Now, here in
yes,
this
yes.
example, our sample space is restricted. And that is why in this scenario, these two events, if we talk about event A and B, then these are disjoint events. But in your case, if the sample space is natural numbers, then getting multiple of 5 and getting multiple of 3 at a time simultaneously, these two events can occur. So in this scenario, they are not disjoint.
Okay,
Okay?
ma'am.
Fine.
Yes, ma'am.
So let's proceed now with probability of independent events. Okay? So, probability of P A intersection B is given as probability A times probability B. Right? Probability of A intersection B is given as probability of A times probability of B. Let us see one example. Suppose we win the game if we pick a red marble from a jar containing 4 red and 3 black marbles, and we get heads on the toss of a coin. So what is the probability of winning? So what is the winning condition here? What is winning condition? If we pick a red marble from a jar, so jar contains 4 red and 3 black marbles. So 7 marbles are there in the jar. So if we pick a red marble from a jar and if we get heads on the toss of a coin, then this is a winning condition. Okay? And what we want is, we want to find out the probability of winning. Yes. Got the problem?
Yes, ma'am.
Fine. Now, see here. What is my event A? Event A is getting a red marble from the jar. That is my event A. What is my event B? Getting heads on the toss of a coin. Getting heads on the toss of a coin. That is my event B. Now, what we need is, we need to find out the probability of both getting a red marble and a heads in a coin toss. So both we should get. And if we are getting both of this, then only we'll say that we are the winners. Okay, so we need to find the probability of both these events, getting a red marble and heads in coin toss. So, what is probability of A? Probability of event A. The event is getting red marble from the jar. We are having 4 red and 3 black marbles in the jar. So overall, we are having 7 marbles in the jar. Out of these 7 marbles, 4 are red. So probability of getting a red marble from the jar is 4 divided by 7. Okay, and probability of getting heads on the toss of a coin is obviously half. 1 divided by 2. Right, so 50% of times it is possible that we are getting the heads, and 50% of times it is possible that we are getting the tails. Toss of a coin, right? So probability of A is 4. Probability of A is half. So if we want to find out the probability of winning, then what we need to do? See here, we know that there is no effect of color of the marble on the outcome of the coin toss. Right? So the first event is I'm picking up a marble from the jar. So what color of marble I'm picking up, it has nothing to do on the outcome of the coin toss. Right? So these two are independent events. And probability of A intersection B is defined as probability of A into probability of B. So we are computing here probability of A is 4 by 7 and probability of B is half. So the probability of A intersection B is 2 by 7. Probability of A intersection B is 2 by 7. Right, so probability of independent events is denoted as probability of A intersection B, and it is the multiplication, it is product of probability of A and probability of B, that's all. Right, so here the probability of winning is 2 by 7. Right?
Yes, ma'am.
Fine.
Yes, ma'am.
So let's proceed now with probability of dependent events. So we have seen independent events. Okay. Now, what are dependent events? If the outcome of event A is affecting the outcome of event B, then we say that these are dependent events. Okay. Now, let us say that event A is getting a red marble from the jar. We then keep the marble out. That means we are not replacing that marble. And then take another marble from the jar. Right? Now, will the probabilities in the second case still be the same as that in the first case? That is the question. What we are doing? We are having a jar and we are having the marbles in the jar. So we are getting a red marble. Event A is getting a red marble from the jar. Okay, so suppose we are having say 4 red marbles and suppose 3 black marbles. So what is my event A? My event A is getting a red marble from the jar. Now, What we are doing is, this red marble that we have drawn from the jar, we are keeping it aside, right? We are not once again replacing it. So if we are not replacing it, then next time what would be there in my jar? I'll be having 3 red marbles and 3 black marbles. Right? And then I'm taking another marble from this jar now. So whether the probabilities in the second case still are the same as that in the first case? Yes?
No.
Obviously not. Okay? So for the first case, the probability of getting a red marble is 4 divided by 7. Because total we are having 7 marbles and 4 are red marbles. So probability of getting a red marble is 4 by 7 in this case. Right? But now let's assume we have got a red marble on the first attempt. Right? Now for second attempt, to get a red marble, the probability is now 3 by 6. So this is the probability of red marble, and this is also the probability of getting a red marble. In the first attempt, the probability of getting a red marble is 4 by 7. And if we assume that in the first attempt we have got the red marble, then probability of getting the red marble in the second chance is obviously 3 by 6. Because now in my jar we are having 3 red and 3 black marbles. So obviously probability of getting the red marble is 3 by 6. Is that correct? But this is another situation. See, if in the first attempt we have not got the red marble, but instead we have got the black marble. So in the first attempt, if we have got the black marble, then in the second attempt, if we have got this black marble, then obviously in my jar now, what I'll have 4 red marbles and 2 black marbles. Right? So if I have got black marble in my first attempt, then this is the position of my jar. Right? So in my first attempt, I have not got red marble. Now, what is the chance that in the second attempt, I'll be getting the red marble? Obviously, in the second chance, the probability that I am getting the red marble is 4 by 6. Is that correct? Yes?
Yes, ma'am.
Fine. What is the inference? Here the inference is probability in the second case was dependent on what happened the first time. So if in the first attempt we get red marble, then the probability is 3 by 6 to get red marble in the second attempt. If in the first attempt we have got black marble, then the probability that in second attempt we are getting a red marble becomes 4 by 6. That means the probability in the second case was dependent on what happened in the first time. right? So these events are the dependent events. Got it? Yes?
Yes, ma'am.
Fine. Now, the next concept that we are going to discuss is mutually exclusive and exhaustive events. Mutually exclusive events are the events where two events cannot happen together. If two events cannot happen together, then we say that these are mutually exclusive events. Let us see the example. Getting a head and a tail are mutually exclusive. Getting a head and a tail are mutually exclusive because we can either get heads or tails at a time, but never both at the same time in a single toss of coin. Right? So either we get heads or we get tails in a single coin toss, but it is not possible to get both, and that is why we say that these are mutually exclusive events. Right? One more example. See here, in a throw of a die, this set 1, 2, 3, 4, 5, 6 is an exhaustive collection because it comprises the entire range of the possible outcomes. So we may not have any other outcome other than these 6 outcomes as an outcome of throw of a die. Okay? Now, let us assume that the outcomes even. So this is my sample space, and this is having an exhaustive collection of the outcomes. Okay? Now, let us consider the outcomes of even. So outcome of even is 2, 4, 6 out of this sample space. And if I say not 6 as the other event, then
Yes,
okay,
ma'am. Yes, ma'am.
fine. So we were talking about the exhaustive collection, right? So if I'm talking about a throw of a die, then my sample subspace comprising of 1, 2, 3, 4, 5, 6 is the exhaustive collection. Why? Because this includes all my possible outcomes. Right? And now, if with respect to throwing of a fair die, if I consider two different events, say getting an even number and getting not 6. So, for getting even number, my subspace includes 2, 4 and 6. Right? And if my event is not 6, then my subspace includes 1, 2, 3, 4 and 5. Right? But whenever I consider these two events collectively, so subspaces of these two events collectively, if I am talking about, then I'll be getting this sample space having all the outcomes. So we may say that collectively these outcomes of two events are collectively exhaustive. Right? So this is what is interpretation of mutually exclusive events and the exhaustive events. Okay? So in the next class, we are going to discuss about conditional probabilities. And in fact, in next discussion, we are extensively being using this conditional probability. So we are going to talk about conditional probability in the next session, and then we'll go for Bayes theorem. right? So let's conclude the session today. Thank you.